Let's move to data input, preprocessing, and output for the research pipeline. First, inputs. The first input source is SQL operational data from the IECHMS database used by the portal. The second input source is synthetic pictures generated for repeatable research experiments. The third input source is optional local image folders used for face evaluations when needed. Then pre-processing. So on the server side, database records are mapped into validated research payloads before fast API is called. For attendance images, faces are detected, cropped, and lighting can be normalized before embedding. For forecasting, absenteeism, history windows are prepared. So the chosen forecast engine receives a consistent series. Then outputs. Page matching produces match labels and constraints for manager review. Clustering returns KPIs such as utilization, conflicts, and fairness. Analytics and the closed loop produce plain language advice for weaker and related screens. Managers can download export such as a weekly briefing and advice reliability. The research columnists can also write JSON artifacts used for evaluation tables. Next, I will explain the models and inference process used in this project. For faces, I use pre-trained embeddings and compare FaceNet style, MobileNet V2 and ResNet 50. For rostering, the same input snapshot is sold with CPSAT, a generic algorithm, and a greedy heuristics, so methods can be compared fairly. For forecasting, I use LSTM and random forecast with naive persistent as the baseline and profit only if that optional package is installed. The closed loop runs in fast API and is triggered from .NET through the closed loop from DB endpoint. And all of this is local inference on the research service. There is no third-party cloud machine learning API. Let's move to the testing and evaluation results. I will show the headline numbers on this slide and the matching evidence in the terminal output. On the controlled phase benchmark, the FaceNet style model reached accuracy 1, while MobileNet V2 reached 0.99 with an equal error rate of 0.115. Latency was about 41 milliseconds for the FaceNet style model versus about 21 milliseconds for the MobileNet V2 and CPU. Under capacity stress, CPSAT and the generic algorithm produce zero conflicts while the greedy heuristics produce two conflicts. Forecasting reduced holdout RMSE by about one third compared with naive persistence. In the closed loop, advice stability started to drop from about 10% recognition error. These results were reproduced with an automated verification suite of 33 checks, 24 in Python and 9 in .NET. Now I will show the Python test output that backs up these pipeline results. Now I will show the Python test output that backs up these pipeline results. These are the automated Python tests for the research pipelines. This test RQ3 shows forecasting and prescriptive advice run correctly. The holdout RMSE improvement over naive persistent come from the same analytics pipeline. The RQ4 test shows this supports the closed loop results on the slide. Advice stability is checked across recognition error levels. Next, the RQ2 part. This confirms scheduling works on database shaped inputs and respects participation based staffing demand, matching the stress scheduling comparison on the slide. Overall, 24 Python tests passed with zero failures. One optional perfect test may be skipped if the package is not installed. That confirms the research pipelines used in the demo are working as evaluated. Now I will explain the main experimental findings. The first finding is that integrated SME workflow is feasible. Attendance, rostering, and analytics can work in one portal. The second one is that under capacity stress, optimization methods outperform greedy tools, which is where conflicts appear. The third finding is that learn forecast beat naive persistent on the holdout comparison. The fourth one is that uncertainty should stay visible to managers because advice becomes less stable as recognition error arises. The fifth finding is that operational phase error blending can exceed clean laboratory benchmarks, so human review and careful thresholds remain necessary. Let's move to the limitations and also what remains incomplete for live deployment. Overall, the system met the project requirements with strong performance. The remaining points are evaluation and deployment boundaries, not a failure of the core applications. On data sets, prototype records, synthetic scenarios, and local benchmarks were useful for controlled ARCIC comparison, but they are not multi-site live data and do not cover every decisional photo condition. On models and compute part, comparing pre-trained embeddings was appropriate for the scope, and the models were not fine-tuned on a large geriatric corpus. And on runtime, testing used a local three-tier prototype rather than long field trials. So long-term organizational outcome measures are not claimed. And on decision support, outputs are reviewable, administrator aids with human oversight, not a clinically certified system. Finally, to close this demonstration, the research novelty of IECMH is the uncertainty aware closed loop coupling of attendance, rostering, and auditable advice evaluated for SME elderly care. Not a generic CRET application and not a claim to invent FaceNet or CPSAT in isolation. That contribution is mapped through research questions in one three-tier prototype. Artificial intelligence can support elderly care in parts, but IECMS joins those parts into one usable workflow. Thank you for watching this demonstration.